So hopefully what we looked at yesterday wasn't that bad, dealing with exponential growth or exponential functions. Now, what we're looking at today are essentially the inverse of an exponential function. They're logarithmic. Now, logarithmic functions are very helpful because it helps us solve a lot of exponential kind of equations, where we talk about 4 to the x is equal to a number. Now, if we said 4 to the x is equal to 16, we don't necessarily need an exponential function or a logarithmic function to solve it, because we're just saying 4 to what power is 16? Well, 4 squared is 16, so x is 2. These are nice. Now, not every single exponential is going to be nice, because if we said 4 to what power is 5, well, there's not a nice number that works for this here. Is 4 to the first is 4, 4 squared is 16. So we're looking for some decimal number where x is going to be some number between 1 and 2. And this is where logarithmic functions are helpful, because it gives us a way to find out what x is. And we'll get to those in a minute. But if x and b are positive real numbers such that b is different than 1, then y equals log base b of x. This calls the logarithmic function base b, where we have log base b of x is equivalent to b to the y is equal to x. And we can switch between these two forms. So y is equal to log base b of x if and only if b to the y is equal to x. So this equation's true only if b to the y is equal to x, only if we have both of these here. Y equals log base b to x if and only if b to the y is equal to x. And we have these kind of arguments here, and it's switching from one to the other. Now, for most of these here, especially with log, L-O-G, we can check to make sure that they work. So our first one here, log base 2 of 16 is equal to 4. So our y equals log base b of x if and only if b to the y is equal to x. So I'm going to show you this two different ways. So the first is we look at this here. So we're given this statement. We want to rewrite it as b to the y equals x. Well, our base for this here is the number kind of in subtext in the log. So that would be 2. We put it as the exponent of what it's equal to, which is 4, equals 16. So I just kind of took this here, b is 2, x was 16, and y was 4, and rewrote it as b to the y is equal to x. We switched it from one form to the other. Now, with these here, we can actually check it. Because what we're saying is 2 to the 4th is equal to 16. I can take a calculator and say 2 to the 4th power, and we should get what? 16. We can actually check it to see if this is the correct equation. Questions on this here? Let's look at the next one. Log base 10 of 1 over 100 is equal to negative 2. Now the base this time is 10. Our exponent we'll have is what it's set equal to, so negative 2 is equal to 1 over 100. So 10 to the negative 2 is equal to 1 over 100. And again, in the calculator, we can do 10 to the negative 2. 1 over 100. And lastly, C, log base 7 of 1 is equal to 0. So if we rewrote this, the base is 7 to the 0 is equal to 1. Questions on this here? Okay, we'll come back to it. I'll show you a different way here in a minute. But I want us to go through kind of one way we do both of these switching and then come back to it. So we've gone from logarithmic to exponential. Now we're going to go from exponential to logarithmic. So we're going to go the other way. So now we're going to rewrite it from exponential to logarithmic. Y is equal to log base b of x. So what it's equal to is our exponent. So here the exponent is 4. So we have 4 is equal to log our base, whatever the base of the exponent is, which is 3. And inside the log is what it was equal to for the exponential. So for 3 to the 4th equals 81, we have 4 is equal to log base 3 of 81. And that's it. Questions on this here so far? Now the next one we have is 10 to the 6 is equal to 1 million. 10 to the 6 is equal to 1 million. So if we're going to rewrite it, what it's equal to is the exponent. So 6 is equal to log, our base this time will be 10 of 1 million. Bless you. Bless you. Questions on these so far? Now, with checking these, because I didn't say it on the first one, didn't say it on this one, but there is a log button on the calculator, and it's written in common logs, and we'll get to explaining what common logs are, but we can't just type in this here and be the same as log base 3. There is a way to type them in, and we'll go over those here in a minute. Now we look at the last one, C. 1/5 to the negative 1 is equal to 5. Again, we set it to the exponent, so negative 1 is equal to log base 1/5 of 5. Any questions on any of these here? What you good with these here so far? Yes? Okay. Now before we get to those, I'm going to add a little bit here. Now this is probably going to go after this next one, but I'm going to do it before it, because there are certain properties that are nice to know. The first one, log base b of 1. Log base b of 1 is equal to 0. No matter what the base is, if we have 1 inside the logarithm, it's going to equal 0. And the reason for this is if we rewrite this as an exponential, because that would be b to the 0 is equal to 1. Because if we rewrote log base b of 1 as an exponential, we would have b to whatever is equal to equals 1. Well, the only way we can have anything to an exponent and it equal 1 is if it is the exponent to 0. Because anything to the 0 power except for 0 is 1. So if we have 1 inside the log, no matter what the base is, it's going to equal 0. The next one we have log base b of b is going to equal 1. Whenever the base and what's inside the logarithm are the same, it equals 1. And the reason for this is that we have really b to the 1 is equal to b. I can put parentheses around it just to make it make a little more sense. So we have log base b of b to the x. Log base b of b to the x. Well, log base b of b is 1. Log base b of b to the x is going to be whatever that exponent is inside the log. But really what this is saying is our base to what it's equal to is equal to what's inside, which is going to be b to the x. And our last one, b to the log base b of x is equal to x, whatever's inside the log. Because that b to the log base b, when we have those matching, the log will essentially simplify out. And if we wrote it as an exponent, or not, and we change it to exponential form, we get log base b of x is equal to log base b of x. Now, out of most of them, these two here are very nice. These two here are very nice. Because if log base b of b to the x, when the b base and what's inside are the same, we can simplify it. And we'll get to a lot of the properties, especially why this works. But for more or less explanation, this here, the power rule, not power rule, but the exponent rule of logarithms, the exponent comes out, and we have log base b of b, simplifies, so we just get the x. And b to the log base b simplifies and leaves what's inside. So questions on this here? For most, this isn't anything new. We haven't covered this yet. Now, the reason I say this and point this out is because if we come back to these here, I'm going to look back at these again. So what we've said is, so this here, 2 to the log base 2 of 16. 2 to the log base 2 of 16. The 2 and log base 2 cancel out, giving me 16. And since I put the one side to base 2, I have to put the other, telling us that 2 to the 4th is 16. We got the exact same answer, yes? And this is another way to look at it. Instead of just using the set formula, I can look at the logarithm. And in this case, for the second one, the logarithm's base is 10. So I can put both sides to this base of 10. Here, these will cancel, leaving us with 1 over 100 is equal to 10 to the negative 2. And we could have flipped it. We could say 10 to the negative 2 is equal to 1 over 100. But it's the exact same thing. And the last one is we can put both sides to the base of 7. So 7 to the log base 7 simplifies out, leaving us with just 1 is equal to 7 to the 0. And really, this property is really what we're doing in going from here to here. is applying that base b to both sides. Well, log base b of b to the x is just x. Here we have b to the y. Questions on this here? Now we can do a similar step for this here. Because one of the properties that we just saw, log base b of b to the x is x. We can get rid, if the base and what's inside match up, we'll just get x. So here, the base attached to that exponent is 3. So I'm going to apply log base 3 to both sides. Here, log base 3 of 81 is the same, but here, log base 3 of 3 is gone, and it leaves us with 4. That's it. We could do the same thing for the middle one. But this time we're going to apply log base 10. And this just becomes 6 is equal to log base 10 . We can do the same thing to the last one. But the base is 1/5, so I'm going to apply log base 1/5 of 1/5 to the negative 1. Either way works. Sometimes this method makes a little more sense, because we can actually see what we're applying, what we're doing step by step, not quote unquote magically going from here, well, or magically scrolling, going from here to here or vice versa from one to the other. So sometimes when we actually see what we're doing and applying these properties, it makes them make a little more sense. Questions on any of these here? Okay. Now this next one we're looking at is log base 4 of 16. We want to evaluate it. We want to find out what it is. So one way to do this is we set it equal to x, because we don't know what this equals. Now this one here, and all three of these here are actually quite nice. They're quite nice functions. So what I can do is rewrite it as an exponential. Put both of these to the base of 4. Log base 4 of 16 is just equal to 16, is equal to 4 to the x. Now at this point here, we can say what power of x, or what value of x will make 4 be 16, and that would be 2. Or we can look at this here and see, how can I make the bases be the same? Because we can rewrite 16 as 4 squared is equal to 4 to the x. And according to the bases are kind of one-to-one property, and I'll write this off to the side. You don't have to write this down. B to the x is equal to b to the y if and only if x is equal to y. It's the one-to-one property. Because for me to have two exponential equations with the same base be equal, the only way they can be equal is if the exponents are equal. It's the one-to-one property. So that's all we were doing here, is we got it equal 1-to-1. So if the bases are the same, the exponents have to be the same. And this only works if, at this point here, 16 equals 4 to the x, if I can write it so the bases are the same. If not, it kind of falls apart. Questions on this here? Now, again, there's a lot of stuff we can go into this, because what I could have done, as we said already, 16 is 4 squared, yes? Doesn't this look like our log base b of b to the x? So our x in this case would be our exponent of 2. So it's a lot of how we use the properties. Or the graphing calculator, if we go math and up, log base. It'll actually do it here. Now the normal log button, it doesn't give us a spot to put the base, so it doesn't quite work. So for the next one, B, log base 2 of 8. Now we can set it equal to y. And again, we can use the 2's so that this becomes just 8 is equal to 2 to the y. Now at this point here, you may be able to see what value y is, because 2 to what power is 8? It would be 3. So y is 3. Because we could have gone on in the step before and said, rewrote 8 as 2 to the 3rd. So y is equal to 3. We get this here. So we could have said 2 to the 3rd is equal to 2 to the y. So y has to be 3. And using this one-to-one is nice, especially when we start having variables put in other than the ones we have, or that are not going to be nice. Now we could have also come over here, said math, log base 2 of 8 is 3. Or the last one, log base 1/2 of 8. So we go math, log base, alpha y equals enter, 1/2 of 8 is -3. Now if we worked it out, we could apply 1/2 to both sides. These will simplify, telling us 8 is equal to 1/2 to the x. Now this one here, we can still say 8 is 2 to the 3rd. Now the 1/2, I can move the 2 from the denominator to the numerator. We can do that. I can move the 2 up. Essentially, I'm flipping it, 2 over 1. But in flipping this, the exponent goes from being positive to negative, which is telling us 3 is equal to negative x, or x is equal to -3. Questions on this here? And a lot of these are coming from manipulating these properties of logarithms and working with them so that we get something that does work. Now we will go into more of the properties in 4.4, because there are 3 other properties, our multiplication, division, and exponent properties, and we'll get into those there. Now the logarithmic function, base 10, is called the common log, or common logarithmic function. The common logarithmic function is denoted as y equals log of x. Notice that the base 10 is not explicitly written. That is, log base 10 of x is written as y equals log of x. We don't have to write the base 10 in. So we look at the graphing calculator and we hit just the log button. This is considered to be common log, so it's a base of 10. So if we do have a log, we already had one already. This one here, 10 to the 6 is equal to 1,000,000. We wrote it as log base 10 of 1,000,000. Here, I can put 3, 4, 5, 6, and we do indeed get 6 because the base is 10. If the base is 10, we don't have to do log base. It's already there for us. Now, the other logarithmic function we have is the natural log. The natural logarithmic function is denoted by y equals ln of x. And the base for this logarithmic function is e. So anytime we see ln of x, the base is understood to be e. Or really what we're saying is y equals log base b e of x, but we just write it as ln of x. Now, I don't know why it's not in L, because natural log in L instead of ln, don't know why. Don't know why they flipped it like that, but that's what they've done is ln, because log, log, makes sense, but ln, it's to the base e. And e is not a nice number. We saw it yesterday. So e is this here, this irrational number. And sometimes it's very helpful using ln instead of logs. So if we want to evaluate any of these here, we can actually just use a calculator. Now, the book definitely says to use our one-to-one property, rewrite it in exponential form, and then go that way. Or here, log of 100,000, I could say log 2, 3, 4, 5, enter, and we get 5. So with tens, yes, because really what we're saying, 10 to what power is 100,000. Because each time we increase the power for 10, we're just adding another 0. So here, if we're taking away zeros, 1, 2, 3, this should be, and we can say log 0.001, and we get -3. ln of e to the fourth. ln of e to the fourth is 4. ln of 1 over e. ln of 1 over e. Now, I'm going to go on and hit enter. It's going to give us an error. I'm going to tell you that just from the get-go. Because if you notice, e, when I hit it each time, it gives us a little box. I'm going to go on and hit enter. Syntax error. E needs an exponent. E always needs an exponent if you type it into the calculator. Now, when we write it out as e, if it doesn't have an exponent, that's fine. We can write it as e. We have no issue with it. But if e doesn't have an exponent, the exponent's understood to be what? 1. So I still have to put into the calculator an exponent of 1 with e, because the calculator is expecting there to be an exponent. It's not just going to assume it's 1, it needs it to be told. We need to tell it that it's 1. Questions on any of this here? Now, one thing that you can have, and this is, again, one of the properties, ln of e is 1. Just the natural log of e is 1, because the base of the natural log is e, and as we said already, log base b of b is 1. And in kind of an easy way I've thought of this, or think of this, if I make it look like a 0 or an O, ln of e is 1. But here, ln of e to the 4th, we just take the 4th power with it. Okay. Exponential and logarithmic functions, especially with graphing and working these out, you kind of have those properties. We looked at the logarithmic or exponential functions yesterday. The domain is all real numbers, negative infinity to infinity. The range was 0 to infinity. If it's increasing, if we had negative b to the x, it flips. We've seen that. Horizontal asymptote passes through 0, 1, increasing, decreasing. Now for logarithmic functions, again, we said they're inverses. And as we talked about inverses, the domain and range flip. So now the domain is from 0 to infinity, because our range was 0 to infinity. Our range is now all real numbers. The vertical asymptote, x equals 0. Now again, the vertical asymptote, if we have a horizontal shift left and right, we'll move that horizontal asymptote with it. So if we shift the whole function 4 units to the right, the vertical asymptote, which was x equals 0, is going to move 4 units to the right and be x equals 4. Or to the left. It'll move accordingly. Passes through 1, 0, and we have our increasing and decreasing. So the first one we have, log base 2 of x. We want to graph this. And again, the biggest thing I would say is get points. Or we can actually graph it. Because luckily with the graphing calculators, if we go y equals and say math, log base, we have 2 of x. So I can actually type the function in and hit graph. So we have this here. And if we see at x equals 0 at the y-axis, we have a vertical asymptote. Because nothing in this can be 0. Nothing inside the log can be 0 or negative. Nothing inside the logarithm can be 0 or negative. So if we're graphing this, especially in Alex, the first thing I'm going to do is make a horizontal asymptote at x equals 0, y-axis. And from here, we can plot points. Now I can't plug in a value for 0 because it just doesn't work. But looking at the graphing calculator, when x is 1, y is 0. So I do have a point right here. When x is 2, y is 1. So we have 2 points. And if it asks for more than that, if it says 3, the next point I'm going to use is not going to be 3, an x value of 3, because the y value is not nice. It's a non-repeating, non-terminating decimal. They gave us, actually, I think they gave us the approximation of it, but I don't believe that is the entire number. Because we could say, well, they're log base 2 of 3 is, okay, as we see here, we got a lot more decimals than what the graph was showing us. But at 4, we do have a nice number of 2. So we can say 4, 2. So we can find some of these nice points. The next one we have is 8, 3. And at this point, we can tell the graphing calculator, or Alex, to go on and graph it, and we get this here. Domain and range. So the range for this here is going to be all real numbers. The range is all real numbers. Negative infinity to infinity. However, the domain, the smallest value of x that we can have is 0. The biggest we can have is infinity because we're going to the right. Now, if it had been going to the left, it would have been negative infinity to 0. Because if it had been going this way, the domain would have been negative infinity to 0. And do make sure that we do put the smallest one on the right, the biggest one on the left, because this here is not the correct way to write it, 0 to negative infinity. We always put the smaller number on the right, bigger number on the left. Questions on this here? And we do the same thing with log base 1/4 of x. So we can do 1 divided by 4 of x, and we get this here. Now if we notice, the vertical asymptote is still the same. Vertical asymptote has not changed. It's still x equals 0, the y-axis. And as we saw on the graphing calculator, the domain is still going to be 0 to infinity. We still have that right side of the graph. The range is still going to be all real numbers. Now to finally graph it, we just need to get some points. Well, one of them that we have is 1, 0. Now the next one we can plot is 2, negative 0.5. And this is not an approximation. It actually works out to be exactly 2, comma, negative 0.5. Next one we have after that is 4, negative 1. Next one we have after that is 8, negative 1.5. And then we can tell it to graph it. Any questions on this here? Fortunately, unfortunately, however you want to look at it, we're going to end up having to stop here because we're out of time. But we'll finish the rest of this tomorrow.